Hello, my name is Steve Clemens, and I'm a research scientist at the Center for Applied Research at Nova Chemicals. Nova Chemicals is a Canadian-based company and a leading producer of ethylene and polyethylene products for the global market. Ethylene is produced in Alberta, Ontario, and Louisiana, and polyethylene is produced at plants in Alberta and in Ontario. We also operate research and development facilities in Calgary, Alberta, which are focused on all aspects of the materials, from production right through to support of our customers and end user markets. We produce polyethylene products, generally in the form of small pellets, that go into a variety of end use applications, from flexible products such as food packaging to rigid products such as large tanks and drums and articles produced by rotational molding. Polyethylene has been produced commercially since the early 1930s, and it's the most common type of plastic in use today. Polyethylene products are valuable and essential to modern life. For example, consider food waste. Globally, a third of all food that's produced is lost or wasted, and the greenhouse gas emissions associated with this loss is greater than the greenhouse gas outputs of all but 2 countries worldwide. In our globally integrated food supply chains, polyethylene products are vital to producing packaging that enhances the shelf life of foods to minimize waste. That said, plastic pollution is a problem of urgent importance. We are members and contributors to a number of organizations and initiatives that are committed to reducing plastic pollution at the source through programs such as Operation Clean Sweep, which is aimed at eliminating losses of raw materials during manufacturing, during the use and reuse life cycle through programs such as the Closed Loop Circular Plastics Fund, which is a fund aimed at fostering innovations for creating sustainable technologies, and in cleaning up existing plastic pollution through programs such as the Global Alliance to End Plastic Waste and more locally, the Great Lakes Plastic Cleanup. One of the ways to making plastics more sustainable is through ongoing improvement and innovation to promote recyclability of polyethylene products to enable a circular economy. An example of this is producing polyethylene products that can take the place of other materials in packages that are traditionally made of mixed materials. So this image shows some common food packages referred to as stand-up pouches. The demands on these packages is high. They must be durable. They must maintain the freshness of the products that are inside them, for instance, by preventing transmission of moisture or oxygen through the package. They must be rigid enough to stand up, and they also need to be visually appealing. Many flexible food packages are structures with 3 to upwards of 9 layers of materials. Often, some of the design functions are addressed with different materials in the layers. So for instance, there might be metallic foil or other polymers such as nylon. But packages that are made with mixed materials in the layers are not broadly recyclable. So by designing polyethylene products that have the appropriate properties, a package can be made of layers that are all variants of polyethylene, which is broadly compatible in recycling streams. One primary method of producing polyethylene is through catalytic addition polymerization, where monomers are added at a catalytic center to a growing chain. Most polyethylene products are actually copolymers of ethylene with a small amount of a copolymer, typically 1-butene, 1-hexene, or 1-octane that's added. When these monomers are incorporated into the polyethylene, they produce branches that affect the properties of the material. And controlling the incorporation of comonomers is one of the ways to tailor the resin properties for a particular end use. NMR is a primary method for identifying and measuring branching in polyethylene. In a carbon-13 NMR spectrum, there are signals that can uniquely identify any branch from 1 to 6 carbons in length. The diagram in the upper right shows an isolated branch from incorporation of a 1-octane comonomer. And the colored shapes show the correlations of the signals from all carbons of the branch as well as on the main chain up to 3 carbons distant from the branch point, are all resolved in the carbon NMR spectrum. There are some smaller signals in the spectrum, and these are typically from chain ends or from structures where there are 2 branches that are near one another. There is an ASTM method for measuring this by carbon NMR, which involves collecting a quantitative spectrum, integrating specified ranges, and a set of calculations for determining the proportion of the comonomer in the polymer. In the past, we used multiple software platforms for this process. We would use Topspin or Grams for processing the FID and integrating the spectrum. Then the integrals would be transferred to an Excel workbook for applying the calculations. And then those results would be transferred to Word to generate a report. Because the spectra are similar in nature and the quantification methodology is set, this process can and should be automated as much as possible. Spectrus was an obvious choice for this. As I think we all know, it's an excellent spectral processor with very good processing routines, particularly for baseline correction. And it also has reporting capabilities via the integrated ChemSketch. Spectrus processor has a great functionality for creating automation macros, which can perform many of the processing steps, but it can also be used to perform the calculation steps. A major benefit to doing the calculations in Spectrus, as opposed to something external like Excel, is that it eliminates the possibility of making transcription errors when transferring the integral values from one software to another, and it saves time and effort as well. I'll point out here that I'm using ACD's NMR workbook, which is built on Spectrus processor, but the macro functionality is available in many of the ACD products that are built on this platform. Macros can be built up using a variety of no-code and low-code methods, and I typically use a few of them in producing a macro. One way is to open a data set and perform the desired processing steps. All of the steps that you perform are recorded in a history file, and then a macro can be just generated from there. This is often how I start. There are also dialogues which can be used to define the macro line by line. So a command can be chosen from a list, which will spawn a box to define the parameters. In this box, we're getting the absolute integral of the region from 40.5 to 41.5 ppm and storing it in a variable called reg_a. This information can then be used in a calculation. Here's an example where we're using that value that we collected, as well as a couple of other integral values, to in an expression, and we're storing the result of that in a variable that's called O1. Spectrus processor also has user data tables, which are tables of metadata that are saved along with the spectral data as name value pairs, and the names for these are user definable. The information in these name value pairs can be set manually. They can be set through a form, and or they could be set through a macro command. So this command here is taking the value that we've stored in a variable called mol%O, and it's storing it in the name pair where the name is comonomer mol%, and this is being stored as record user data, which is the user data that goes along with the Spectrus project. The code that the dialogues generate is easy to understand, and it can be text edited from within the macro tool. And this can be really useful for copying commands, such as if you have a bunch of integration regions that regions that you're integrating, or if you need to perform similar calculations. With the processed data and spectrum saved together, generating a report is pretty simple. A report template can be set up in ChemSketch with the desired elements in it. So here, one of the elements is the record user data. A report which takes the data from the Spectrus file is generated, and that record user data is included. And then other objects such as expansions, additional text boxes, images, or chemical structures can be added to the report as necessary. There are also macro commands that could automatically even generate a ChemSketch file or even a PDF file as a report. When the Spectrus project is added to the database, the metadata that has been generated goes with it, and the database can be queried on that. Here I'm showing an example where the database is being queried on metadata as well as spectral data. So here I'm looking for any records where the comonomer has been identified as 1-octene, where its level is between 6 and 8 mol%, and where we have a peak marked in the carbon spectrum between 35.5 and 36.5 ppm. This collection of hits can then be examined further or further queried. As I mentioned in the introduction, we're committed to promoting a circular plastics economy. And one of the pillars of this is enabling recycling of the materials and then keeping them in the value chain by using the recyclate. In the next 5 years, the demand for post-consumer recycled resin, or PCR, is expected to increase by 5 to 10-fold. Nova currently sells products that are sourced all or in part from recycled polyethylene to meet customer and consumer appetite for these materials. While mechanical sorting can be quite effective at producing fairly pure streams of recycled polyethylene, one common contaminant in the recyclate is polypropylene. So a carbon spectrum of a PCR polyethylene is shown on this slide. The large peak at 30 ppm is from polyethylene, as are many of the smaller ones. And from looking at this, I can tell that the polyethylene portion of this mixture comprises butene, hexene, and octene resins. But there is another component in here, polypropylene, which is readily identified as shown by shown in the diagram. Its content relative to the polyethylene can be calculated from the integrals of these things. So in a similar fashion as above, we can make macros to automate much of the analysis in these materials as well. While they're not impurities per se, all commercial plastics contain additives to enhance their properties. Some examples of these would be antioxidants or UV stabilizers or processing aids, where they're present often at ppm levels. Many of them are regulated by organizations like the FDA when they're used in food contact applications, so it's important that we're able to measure their content in the material. Polyethylene glycol is an example of a processing aid, and it can be detected and quantified in the polyethylene by proton NMR spectroscopy. Typically, we're wanting to perform these analyses in triplicate and so that we can arrive at an average value. So in this example, there's 3 spectra that are grouped together as a Spectrus project. When they were run, the letter A, B, or C was entered into a user parameter at the spectrometer, which this macro will then use. The macro is applied to each spectrum in the project, and when they're all selected, this can be done with 1 click. And then the calculated additive contents for each one of them is saved in a user data field, which takes where the name is derived in part from that letter that we had put at the spectrometer. When a calculation in a macro cannot be done because that data doesn't exist, it throws an error into the macro protocol, and this protocol is a report of the results of each line in the macro. So the macro syntax for calculating an average between 3 runs is shown in the black text here. When I apply this sequentially to the 3 spectra of the project, if I've only applied it to one of the spectra, there are no values for add B or add C yet. So in the macro protocol, it's showing the value for add A, and then there are blanks for add B and C, and that line has resulted in an error. If the macro settings in Spectrus are such that it ignores the errors, then the macro will proceed. This macro protocol is also a good tool for troubleshooting calculations in macros while you're developing them. After the macro has been applied to all 3 spectra, There are values for all three of those variables, and the calculation will return a value instead of an error. So this screenshot here is from after this macro has been applied to all three of the spectra, and we have a value in the name pair peg average. In summary, I've shown that there are time and quality benefits to transferring the NMR data analysis workflow into one software platform. ACD Spectrus was my choice for this platform for its robust spectral processing capabilities and the macro functionality. The macros in Spectrus processor are a powerful low-code way to automate analysis of analytical data from raw data to a final report. Information can be stored together and retrieved easily when the user data and database functionalities of Spectrus are employed, and these processes are valuable for standardizing the quantification of impurities and other components in routine testing. I thank you for your attention.